In this paper, we study the tabletop rearrangement problem in a bounded workspace. Object rearrangement is a basic task in our daily lives. It will be beneficial but challenging to use a robot arm to clean up our kitchens, kids' rooms, food pantries, or office desktops. In rearrangement problem, the robot arm moves objects from start positions to specific goal positions. No matter in home automation or industrial automation, minimizing the number of manipulations directly leads to increased system throughputs. Our paper focuses on tabletop rearrangement with overhand grasps. The start and goal positions lead to dependencies between objects. In the example shown on the right, we need to move the letter I away before moving letter C to the goal. So we say C depends on I in this case. We use a directed graph to represent the dependencies. When the graph contains cycles, we have to move some objects to temporary buffer locations to break these cycles. In this work, we prioritize task sequence computation and delay the allocation of buffers. We first compute a primitive plan. In this phase, we assume there is always a large free space to temporarily place the objects. Computing a primitive plan is equivalent to vertex ordering problems that we studied in previous papers. In the second phase, we look for valid buffer locations inside the workspace, such that all the primitive actions are collision-free. We also introduced techniques to increase the efficiency and the robustness of our method. When there are no valid buffer locations for the primitive plan, we recover from failure by accepting partial plans. The goal arrangement can be found by maintaining a search tree. Besides that, we propose a preprocessing routine for the rearrangement problem. The preprocessing solves an unlabeled rearrangement problem, where the goal positions are interchangeable. This process efficiently simplifies the dependency graph and further speeds up the computation. Compare our methods with other state-of-the-art approaches with various practical scenarios. In large-scale problems, our method generates high-quality solutions much faster than other algorithms. For extremely dense instances, our method is the only one maintaining high success rates. For 15 puzzle problems, our method is also more scalable than other methods. We also set up a hardware platform to execute the plan we computed. The black area indicates the bounded workspace for rearrangements. Our TRLB framework computes high-quality plans efficiently. Method can also solve rearrangement problems with objects that are densely packed up and with concave shapes. Thank you for listening.